recording. Okay. Looks like the session's being recorded. Somebody's got their mouse pointer on. Okay, session's being recorded. We're live. Welcome back to Statics. Hope everybody had a great weekend. Let me talk a little bit about some announcements just so everybody's on the same page. So I wanted to be clear. I had some emails today about the exam. If you remember, I moved the exam because of how we rearranged the topics. So the exam is going to be on Wednesday, November 18th. What we'll do is we'll do our review the Monday prior to that. We'll have the exam on Wednesday, and since that Friday is the Friday before Thanksgiving break, and since we're doing so well on timing, we might actually, once we get through some of these topics, be slightly ahead, that we can go ahead and cancel class. And then when we come back during dead week, we'll do friction for Monday and Wednesday, and then have our comprehensive final review on Friday. So with that, let's go ahead and get right back into it. And today what we're going to do is sort of finish up centroids. I guess technically we are already finished with centroids because we've covered everything that there is to cover. We've covered centroids of lines, of areas, of volumes. We've even done some applications. And then there was this moment of inertia concept that showed up after. And with moments of inertia, it's technically a separate topic, but as you'll see, especially after the example that we do today, it's just such a natural extension of what we've been doing with centroids that it seemed to be a good thing to cover. Let's start off by just making sure that we're clear on the background. So, you know, we've got here sort of a calculus-based perspective of what we've done when defining these properties. So, we introduced this sort of shorthand notation for the integrations that we perform with respect to areas and centroids. That little integral of dA just means that we're just summing up all of those little rectangles across a region, and so that's how we compute the area. And then we said, well, we can also define moments of area. So this would be the first moment of area, and this would be the second moment of area. The first moment of area was really useful when we determine the centroid, right? Because we could say that the integral, let's say, of x dA divided by the integral of dA, we have a name for that. We call it the centroid, right? And so that first moment of area had a use, right? We're not just integrating for the sake of integration. The second integral of area also has a use. We have a name for that, or sorry, not the second integral, the second moment of area also has a use. We have a specific name for that. We call it the moment of inertia, and it has a very profound impact on structural response. So, and we talked about that last time. The example of, if you're framing a deck in your backyard, that we orient the joists a certain way because the beams are stronger in that one direction than they are in another, or stiffer is the more appropriate term. We did an example last time where we looked at it was very quick. We basically just used these integral expressions to compute the moment of inertia of a generic region. And what I want to do is develop a more general approach and a more practical approach for real-life scenarios that engineers experience. The first thing I need to do is I need to talk about moments of inertia of simple shapes. And so what I mean by that is, what's the moment of inertia of a rectangle? What's the moment of inertia of a circle, and so on and so forth? We can use these calculus-based approaches to derive an expression for a moment of inertia, and it's really easy. So, for example, let's take this rectangle. So how do we do this? So we're ultimately worried about, let's say we're trying to find the moment of inertia with respect to the x-axis. Ultimately, what we're trying to do is complete this integral, the integral of y squared dA. And so we need terms for these expressions. So first off, we look at dA and we ask, okay, what is dA? Well, if we're talking about, if we go down here and we look at the region that's shown, if we're talking about this little strip, rectangle that you see with respect to the y-axis, what is the area of that little rectangle? Well, it's the width of the beam B times some thickness dy, right? And so how do we evaluate this integral? We're integrating, what is it, y squared dA? Well, dA is d dy, so we're integrating, y squared times b dy, and we're integrating across the entire rectangle. So we would say like minus h over 2, positive h over 2. And that's basically what I have right here, is I'm just following that out. And if you go through all the the alphabet soup and chug it out, what you get is a very famous equation. I think just about every engineer should remember this equation, that the moment of inertia of a rectangle is bh cubed over 12. Now, if you notice here, my notation here, I'm doing something a little differently. Instead of writing I sub x, I write I sub c. Okay. So what's the deal there? The deal there is that if you look here at the description, what I'm doing is I'm computing the moment of inertia, and I'm doing it with respect to the centroid. Okay, if you notice, look at the coordinate system that I've got drawn here. You can see my x-axis, this is my y-axis, and note where the origin is. The origin is at the centroid of that rectangle. If you were to recompute this a little differently, so for instance, let's say you wanted to compute the moment of inertia, let's say, of a rectangle. So here's your rectangle, but you placed your axes like here, like that's your y-axis and that's your x-axis. Well, if you place your axes there and you try and compute, well, what's the moment of inertia of this rectangle in this scenario, you're going to get a different answer because your coordinate system is in a different spot. See, the formula for the moment of inertia is the integral of y squared dA. So it is dependent upon where your coordinate system is. And so maybe one of the questions you might ask is, okay, where is the most appropriate spot to place that coordinate system? And I'd argue for most practical applications, the centroid is where you would place it. And so we have to talk about how to approach that for a generic problem. Now, before we get there, we need to look at the following slide. This is a reference for some moments of inertia. So first off, this is in your book. It's in chapter 9. We're actually sort of skipping ahead in the book. Chapter 5 deals with centroids, and chapter 9 deals with moments of inertia. So if you open up chapter 9, you'll find this reference. You'll also find it in the back cover of the textbook. Remember, the back cover listed formulas for centroids. It also lists formulas for moments of inertia as well. And if you notice, this is kind of what I was talking about. So let me see if I can highlight this. If you look right here, let's take the rectangle. If you look at the rectangle, you'll see these formulas right here. And these formulas are the ones that we just derived, the bh cubed over 12. And then there's also a flip side. So the moment of inertia with respect to the x-axis is bh cubed over 12. With respect to the y-axis, it's b cubed h over 12. You sort of flip your dimensions of your rectangles there. But if you also look, you can see there's actually two sets of formulas listed. There's one for the with respect to the centroid, and then there's another set of formulas with respect to the corner. See, if you look at the image here, you can see what I'm talking about with respect to your coordinate axis. You can see this coordinate system here. This one's you can see this one's at the origin. You can also see this one right here. Oh, that didn't actually go very well. Let me sort of draw that again. So we have one set of coordinates with respect to to sort of this lower left corner, and we have another coordinate system with respect to the centroid. Sometimes these guides list different formulas dependent upon how engineers like to compute the moment of inertia. I'm going to show you a little bit of a general approach that I like to use here in a bit. But you always want to be careful and make sure that you're using the right value when you do your computations, and that'll become clear as we do an example here in a bit. So always make sure that you're paying attention to which value you use and what coordinate system it's referencing. And don't worry, I've got a really comprehensive example on that. Now, what I ultimately want to do is I want to develop an approach to be able to compute the moment of inertia of a shape like this. This is the one we're going to do here in a bit. And this is something that's very relevant to what an engineer would deal with. This is the moment of inertia of a composite shape that you could probably see how we're going to approach this. We're going to take this this region, And we're going to split it up into a bunch of simple shapes, right? And when you split it up like that, you can see, okay, I've got a triangle, I've got a rectangle, I've got a circular hole, I've got a semicircle. So it's going to be a lot like a centroid calculation. There's a little bit more going on, but I'm going to be able to follow the same process. But the algorithm is a bit different, okay? And I kind of want to show you how that works. And I've got a lot of stuff coming up on a slide here in a second, so I want to sort of take a step back and show you how this works. Let me stop the share. I'm actually going to try a little tool here on Blackboard. Let's see if this works. Okay, so let's see if this works. Okay, so I want to show you how we're going to go about this, and I want to kind of derive this expression for you. So I want to go first off to the basic formula, and I'm just going to use the formula with respect to the x-axis. It really doesn't matter which one you use because you get the same result either way. But let's look at the moment of inertia formula with respect to the x-axis. And so that's going to be the integral of y squared dA. Okay. Now, what we need to be able to do is we need to be able to compute moments of inertia with respect to different coordinate systems. And so what that ultimately means is shifting the axes some distance. So what I'm proposing is, this would be the basic formula for the moment of inertia with respect to the x-axis. What if I wanted to compute a moment of inertia with respect to some new axis? Maybe we'll call it x prime. And so I propose ultimately what we're doing here is we're taking the integral of not y squared, but y plus some distance. And I'm just going to call it d just to keep this simple. I didn't want that to happen, but I kind of had a feeling it would. Sometimes this pen's a little strange. So ix is the integral of y squared dA, and then for x prime, so I x prime, what we're doing is we're integrating not y, but y plus some increment. So the idea behind that is, if I did it again, I didn't mean to do that, my apologies. So let's say I have some shape out in space that I want to compute the moment of inertia of. The idea is I might have the moment of inertia with respect to some axis, and so now what I want to do is I want to find the moment of inertia with respect to another axis. So maybe this is the third time's a charm. So my new value here is the integral of not y squared, but y plus some distance. And that's supposed to be a parentheses. I'm not erasing it. That's supposed to be like some parentheses like that. Okay. And what I'm talking about with the distance, I'm basically talking this value here, this distance value. Now, in order to derive this formula, what we have to do is we have to expand this a little bit. Now, if you were to take this term y plus d and then square it, it's not y squared plus d squared. You got to FOIL that out, right? Because you've got y plus d times y plus d. And that's going to be what? Y squared plus, and then you have dy and dy, so you've got 2 dy plus d squared, right? So if I were to expand this, I might have the integral of y squared dA plus maybe say 2d times the integral of y dA plus the integral of d squared a. Sorry, d squared dA. So what I can do is I can sort of rewrite this a little bit. So this integral right here, that's just the original ix. I'll get to this middle integral here in a second, but this integral that you see here over on the right, if I factor out the d squared, I have d squared times the integral of dA, and that's just the area, right? Now, as for this integral in the middle, what I have here is I have 2d times times this, okay? And if you remember, that's a first moment of area. And we use that first moment of area to determine where the centroid was. Well, if we place our new coordinate system where the centroid is, then this whole term is going to go to 0, okay? And so what we're going to be left with is ix plus ad squared, okay? And so I kind of wanted to show you where this formula is coming from that you're going to see here in a second. And this right here is ultimately the algorithm that we're going to use in order to compute the moment of inertia of a composite shape. Let me go back to the slide here, and you'll kind of see what I'm doing. So the idea is here is your base formula for the moment of inertia. And if you want to find the moment of inertia with respect to a new coordinate system, basically you're assuming those coordinate systems have parallel axes, hence the ParallelAxis Theorem. And so once you expand that out, you find that the first integral is with respect to, or the first integral, because you end up having 3 integrals, the integral is just your original moment of inertia. The third integral is just ad squared, and the one in the middle references the centroid, and if you put that coordinate system at the centroid, it's going to be 0. And so what you leave with is the following formula, which is the ParallelAxis Theorem. And so the idea is that if you want to find the moment of inertia of a composite shape, what you do is you sum up these terms, I plus ad squared. I being the moment of inertia of each individual shape, or the simple shapes, A being the area of the simple shapes, and then this term d squared. What we do is we define d as the distance from the centroid of each individual shape to the centroid of the whole thing. Actually, these are the easiest ones to find. I know sometimes they tend to confuse students when you first start doing this, but they're actually pretty straightforward. I think that the easiest way to understand this process is to use an example. So I want to look at the following example. This example is actually much more complicated than the one that I gave you on your homework assignment. The one on your homework assignment is just rectangles. It's kind of akin to an I-beam. It's actually not, it's a C shape, but it's very akin to that. But the idea is we're going to compute the moment of inertia of this composite shape with respect to the centroidal x-axis, because that's the one that's going to be relevant. So the first thing that we're going to need to do is actually find the centroid, and then we'll compute the moment of inertia. And I'll kind of show you how that works. It's a pretty straightforward process once you get the hang of it, and it borrows a lot on what we've already done. So let me stop share and bring up the notebook here, and let's just sort of dig into it. All right, so share screen. Okay, so all right, so here's our problem here. And let me put my screen down here so we can follow along here. So like I said, what I'm going to do is I'm going to take this problem and I'm going to split it up into 4 regions. So I've got this and this. Okay. Now let me go ahead and just make sure that we describe these regions. So I'll say simple shapes. And so we'll number them. So I propose there's going to be 4 shapes. Okay, so shape 1, shape 2, shape 3, and shape 4. Okay, so shape 1, and let's number these in order of increasing complexity. So the first one we'll just say is the rectangle. And then maybe we'll say this is the triangle. This is the semicircle, and this is the circular hole. Okay, and maybe another thing I ought to do is throw some sign conventions on here. This is probably pretty straightforward at this point. In other words, that's going to be treated as positive area. That's going to be treated as positive area, but that one's going to be negative. Right, the hole. I'm taking material out of the section. Okay, Before we jump right into this, let's go back to how we would set this up as a centroid, okay? So let's say I wanted to find the centroid of this region, okay? Notice how one of the things I didn't give you was a coordinate system. There's not one there. So we kind of have to place a coordinate system on here for reference, okay? And so maybe what I'll do, just for the sake of discussion, is maybe I'll do this. Maybe I'll say, let's put the coordinate system, I don't know, right here. Just so we have something to go off of. Ultimately, where we place that coordinate system isn't going to matter. We're going to compute the centroid with respect to this coordinate system, but what we're going to find is when we compute our d distances, we sort of remove the location from the process, and that'll become clear as we get into this. Okay, let's take each shape one at a time, and let's see what we can derive. So let's look at shape one. Okay, so shape one is a rectangle. Okay, now rectangle. I don't know what happened there. Okay, rectangle. All right. Now this rectangle is, as you can see here, what do we know? We know its width is 10 inches. And we know its h is, what is its height? What is the height of this rectangle? Let's see if we're paying attention here. Anybody know how tall this rectangle is? It's 8 inches. And the reason it's 8 inches is because of the semicircle. The semicircle is has a radius of 4 inches, so the height of that is 2 there. Now I noticed what Mr. Fishball was saying. The 3 inches is just to where this hole is, and that hole could be anywhere. All right, so this is 8 inches. Now what I'm going to do for this rectangle is I'm going to compute 3 properties. Okay, the first thing I'm going to compute is the area. Okay, and that's easy. That's just going to be BH. Okay, and 10 times 8, that's easy. That's 80. Okay, that's easy. Okay, the next thing I'm going to do is I'm going to compute, the y distance. So whenever you're computing the moment of inertia with respect to x-axis, you need your y distances. So maybe what I'll do is I'll say that, you know, we're saying Ix is the sum of I plus AD squared. And whenever you're doing these d distances, you sort of flip your subscripts, and we're computing these y distances, right? And that shouldn't be that hard to follow. I mean, the moment of inertia with respect to the x-axis from a calculus perspective is the integral of y squared dA. So you always flip that. So let's determine y. So somebody help me out. How far is it from the x-axis to the centroid of that rectangle? Remember, we're just looking at each individual shape. 9 inches. So we're going the x-axis. Yeah, 4 inches. There you go. Yeah. So ultimately, what we're trying to find, just so everybody's clear, if this is the shape, we have a hole here. We're trying to find out like where the centroid is. So we're ultimately trying to find like y bar. That's what we're trying to find out. So we're trying to find these vertical distances. All right. So this is 8 over 2, which is 4 inches. Okay. So there's that. Now we've got the new formula we got to figure out, which is this moment of inertia. Now what I'm going to be using is the moment of inertia with respect to the x-axis, and between these two, if you look at the rectangle, I've got like an Ix bar and I've got an Ix. I'm going to use the Ix bar. I want the formulas with respect to the centroid, and so the formula is going to be 1/12 BH cubed. Okay, so that's what we computed before, the BH cubed over 12. So this is 1/12 of, what is that, 10 inches and then h is 8 inches, and then that's cubed. We're cubing the 8. Okay, so somebody help me out. What do you get when you plug and chug this? Write that again. There we go. 426 points. So we'll give it one more decimal. 426 point. We'll say 67. Now let's talk about units. And this might be a little strange the first time that you see it. The units for a moment of inertia are going to be like length to the 4th. So it's like inches to the 4th. And the idea is you're taking like a second moment of area. So you're taking area, multiplying it by a distance, but you're really multiplying it by a distance squared. So that's why the inches to the 4th comes away. I know that the unit might seem a little strange, but that's just sort of something you got to get used to. Okay, these are really the 3 values I need for each shape. So let's move on to the next one. So the next one is a triangle. Not really, but you could, you could kind of think of it that way. The 4th dimension. Okay, so let's. All right, so the question was, where is the height 3 inches or the 8 inches? What we're talking about here, this is sort of a dimensional thing. So if you look at the rectangle, like right here, next to that rectangle is a semicircle. And that semicircle has a radius of 4 inches. So what is this dimension? It's 2 times the radius. That's where we got the height of the rectangle to be 8 inches. Does that make sense? No worries. No, the circular hole isn't dead center. That's the point. It's a little off. Okay. Let's look at this triangle. So just like with the rectangle, the triangle has a base of 8 inches, but it also has a height of 8 inches. Okay, so let's handle that. So we know the area of the triangle. How do we compute the area of a triangle? It's 1/2 times the base times the height. So this is going to be 1/2 of 8 inches times 8 inches. And so 8 times 8 is 64, divided by 2 is 32. Okay. What about the y? Okay, so help me out. If we agree that this dimension is 8 inches, then help me out. Where is the centroid? How far up from the x-axis do we have to go to get to the centroid of that triangle? Exactly, h over 3, right? So 1/3 of the height. Remember, triangles, the centroid is 1/3 up. So this is 1/3 h, so 1/3 of 8 inches. And so that's 2.67 inches. Okay, exactly right. And as for the moment of inertia, again, we're using the moment of inertia as the centroidal one. And so I'm going right here, I'm using that formula. And so that formula is BH cubed over 36. Okay, and that's why these references are so valuable, because I'll be honest, I mean, I do this every day, and even I have a hard time remembering all these formulas. That's why we have these references. So it's 1 over 36 BH cubed. Okay, so the 1 over the 36, so 1 over 36 times 8 times 8 cubed. Somebody help me out in the chat. What's that going to be? $113.78. Exactly right. Okay. Moving on. Okay, so so again, you just keep doing this for each shape. Okay, so the third shape is this semicircle. And the semicircle has a radius of 4. Okay, so a couple of these properties should be pretty easy. Okay, so first off, the area. How are we going to determine the area of a semicircle with a radius of 4? Well, it's just 1/2 pi r squared, right? So 1/2 pi r squared, 1/2 is that. We have pi. That's 4 inches. Sorry, 4 inches. 4 inches squared. And so let's see. That comes out to be, I think it's like 25.13. And just so everybody's clear, once we get finished with this, we're going to take this problem, we're going to arrange all of this data in one big table, very similar to what we did with centroids. So it's going to be, I wanted to try and do this problem a lot like the problems that we did in the past. So, okay, why? This is where I need your help. Let me scroll up a little bit. How far is it from the x-axis if we're traveling vertically? What's that y distance to get to the centroid of that semicircle? And so this, to be clear, this isn't the 4r over 3 pi thing. See, it's not 3. Remember, this semicircle has a radius of 4 inches. It's 4, right? Here, so you can see right there, that's where the centroid is, right? And so we're asking ourselves, how far is that distance? And that distance is just going to equal the radius in this case, which is 4 inches. Remember, you always reference that with respect to that horizontal line. Okay? This is going to be r, and that's going to be 4 inches. Not to say that it's always 4 for, or it's not always r for every problem. It's just how far is it from the datum that we chose, from the reference coordinate system. Okay? Does that make sense? Because I know there's been a lot of people who've been answering 3s and whatnot in the chat, and I want to make sure that's clear. Sorry, that drawing is admittedly not clear. Let me draw it like this. That's where the centroid is. This distance here is 4 inches. Everybody good on that? Okay. All right. Now let's do IX. Okay. And fortunately for this problem, that's actually going to be kind of easy. But one of the things you have to be careful about is that you're picking the right value from the table. What I mean by that is this, okay? The table lists the values based on the shape looking like this. But in our world, the shape looks like that, right? Because the semicircle, as you can see, it's rotated 90 degrees. So theoretically, what you would have to do is flip them, right? So before we were looking up IX values, we'd have to look up the IY value for the semicircle because the shape is rotated. But it actually doesn't really matter for this problem because IX and IY are the same thing. And as for referencing it with respect to the centroid, remember the y-axis, or as you can see here, it's going right through the centroid. So because the y-axis is going right through the centroid, we don't really have to worry too much about, well, whether the formula is right because it's already referenced that way. So this is going to be 1/8 pi r to the 4th. Okay, and let me erase this because I'm running out of space. Okay, so this is going to be 1/8 pi, and that's 4 inches to the 4th. Somebody do that one for me. What'd you get? 100.53. Good deal. And lastly, we have this circular hole. Now remember, when we insert the values in the table, they're going to have the areas and the moments of inertia are going to have to be negative. Now, let's first off go back and let's refresh our memory. What do we know about the hole? The hole has a 3-inch diameter. So if the hole has a 3-inch diameter, its radius is 1.5, right? Cut the diameter in half to get the radius. So the area is pi r squared, pi times 1.5 squared, which is 7.07, right? Now, this is where I want everybody to pay attention. What's the y? Well, yeah, it's going to be negative, and I'm going to indicate that here in a second. I was going to put like a negative right there. But you are correct. You are absolutely correct that area is negative. But this is where I want everybody to pay attention. What is the y distance for this hole? It's 5 inches. That's exactly right. From the x-axis, go vertical, it's 5 inches. That's exactly right. Okay. Now, last thing we need is the moment of inertia. For a circle, that's really easy. Just about every one of your guides will give that with respect to the centroid. And because it's a circle, it doesn't matter whether you use the IX formula or the IY formula because they're all the same. And it's going to be 1/4 pi r to the 4th. Hold on. Can you explain how it's 5 inches? Yes. Okay. So here's the shape. So here's the shape, and what we were given for the problem is we knew that the radius of this was 4 inches. Okay, and if we know that the radius of this is 4 inches, we then know that that is 8 inches. Well, what we were told about this hole, which is like right here, we were told that this dimension was 3 inches. And so if this is 3 inches, what we're ultimately trying to figure out is what is that. And so what is that? It's 8 minus 3. So that's why we're here. This is really important. Yeah, this is really good stuff. I'm really glad that we're going through all this. Okay. If y'all have any other questions, like let me know. Okay, so this is 1/4 pi. That's 1.5 inches to the 4th. And so let me know what this equals. .98. That's right. 3.98 inches to the 4th. But this is also negative because it's a hole. Okay. The y is not. The y is actually positive because it's still a positive distance from the y-axis. But the moment of inertia and the area are negative. Okay. Everybody good with the individual values before we start checking out the actual the process, the moment of inertia? Any questions about any of these? Okay, so let me show you how the process works. I'm going to go ahead and preface this in advance. We're going to draw like kind of a big table. It's going to have a bunch of different columns. In fact, it has 7 columns, and I'll show you how this works. Okay, so all right. So first thing we'll do is we'll put the shapes. So we'll have 4 shapes. And we're going to list, so for each of these shapes, we're going to have 6 different data points. Okay, so first thing I'm going to list are the areas. Oh, hold on. Let me do this way. So the areas and the y distances. So I'm cheating here so that I don't have to scroll too much, but here's what we got from our previous problem. We got that the rectangle had an area of 80 and a y distance of 4. We got that the triangle had an area of 32, and this was 2.67. We got that this was 25.13, and this was 4. This was 5, and this was 7.07, but it's negative because it's a hole. Okay, maybe I can squunch this up a little bit on space. Maybe I can do a little better. Okay, so the reason that I'm doing this is because the first thing I want to do is I want to go ahead and compute the centroid and do it now. So we're going to do a sum row down here on the bottom. So if you remember, how do we compute the centroid, right? What's our formula for computing the centroid? We take the sum of AY over the sum of A, right? So I'm going to compute a couple of sums here on the bottom. First thing I'm going to do is I'm going to sum the areas, right? And so if you sum up the areas, 80 plus 32 plus 25.13 plus a negative 7.07, you end up getting something like 130.06. Okay, let me scroll down a little bit so that I'm not squunching here down on the bottom. Hold on. Perfect. Okay, let me move that down a little bit. Okay, so we've got our A's, we've got our Y's. Next thing I'm going to compute are the AY's. Okay, let's go ahead and do that first. So AY, right? So AY, so 80 times 4, that's 320. 32 times 2.67, and you could follow along with me as we do this. You should get something like 85.33, 100.53 for this, and then this one is negative 35.34. So if you sum, oh, I can do better than that. So if you sum this column up, you're going to get something like 470.52. Okay, and so if I wanted to compute the centroid, I would say that that equals 470.52 inches to the third over 130.06 inches squared. And when you chug that out, you should get something like 3.618 inches. And I gotta believe that kind of makes sense. Like if you look at the shape, if we go back up top here and look at the shape, I think it's pretty believable that the centroid is about 3.6 inches from the bottom. I think that's a pretty reasonable conclusion to make. All right. Is everybody with me so far? Any questions before we start progressing? Okay, all right. So now what we're going to do is we're going to compute our moments of inertia. And the way that we do this is we start off by listing our individual moments of inertia. And so usually, like the way I kind of write this is my x naughts, like one of each little shape. Of course, that doesn't really matter. You can call it whatever you want. So we got 426.67. We got 113.78. We got 100.53, and this was negative 3.98. It's just me writing down the values from up above. Okay. Now, in order to compute the moment of inertia, if you remember, the formula was the sum of my i's plus AD squared. Okay. So look at your table, right? We've got the i's, right? We've got the a's. Now we need the d's, right? And we need these d values. We'll call them dy's just to be consistent. Okay. Now, how do I compute these dy values? Right, and I'm actually going to do this. I'm going to give it a little room. This is incredibly easy. Okay. A lot of times students get way too worked up over this. This is really, really straightforward. All you do to compute these is what you're trying to figure out is the distance from the centroid of each individual shape to the centroid of the whole thing. So all you do is take the little y values and subtract y bar. So it's kind of like if you're a fan of statistics, it's kind of like a variance or something like that. You're just taking each little individual y and subtracting the y bar. So this first one is going to be 4 minus 3.618. This one's going to be 2.67 minus 3.618. This one's going to be 4 minus 3.618. This one's going to be 5 minus 3.618. And the thing is, it actually doesn't matter which direction you subtract. In other words, you could do y minus y bar, or you could do y bar minus y. It really doesn't matter because ultimately you're going to take those d values and square them. So whether you subtract one way or another, it really doesn't matter all that much. So when we chug this out, we get 0.38, we get negative 0.95, we get 0.38, and then we get 1.38. Right? Last thing that we do is now we can basically sum up everything. So Ix naught plus AD squared. So all I'm doing for each row is I'm saying, okay, I plus AD squared, right? I plus AD squared, right? I plus AD squared. Pretty straightforward stuff. And so you just take that. So if you're ever a fan of Microsoft Excel, this is a very Excel-friendly problem to do. And so when you chug this first one out, so 426.67 plus 80 times the 0.38 squared, you get 438.36, right? The second one, when you chug it out, it ends up being 142.72. This one ends up being 104.21. And this one, remember, this one's negative because there's a lot of negative terms that go into it. This one's negative 17.48. So the sum is 667.80. And that's it. I mean, it's a lot like what we did with the centroid problem, just a little bit more added on to it. So, I'd say like the way the table is set up, everything on the left side of the table is the central, and then everything on the right side of the table is this moment of inertia. And by the way, what we did was a moment of inertia with respect to a horizontal axis. So we were using vertical distances. A good way to test your understanding is what if we did the vertical axis? Or one way you could think about it is take this shape and turn it 90 degrees and do a moment of inertia with respect to that axis and see what happens. And then maybe a further question, which one do you think will be higher, the x-axis or the y-axis? And I'll go ahead and tell you for this one, the y-axis looks like you'll get a higher answer. In other words, if you take this shape and you turn it 90 degrees, you should get a higher answer. I want to show you something super quick before we call it today. Does anybody have any questions about this? On an exam, should we be able to do the table on Excel to save time? I'm not eliminating that as an option. I'm actually pretty easy to get along with there, but don't let Excel be is what I'll say. And it'll also depend on what we do on the exam. So maybe we'll revisit that as we get closer. The big thing is you'd have to make your sheets yourself. You can't use an old sheet from an old assignment. You'd have to build it yourself. Let me go ahead and pull this thing up on the lecture notes because I really think it's important because I know we're running out of time here. One of the things you'll find in the textbook is this, and this is something that I do want you all to kind of take a look at. This is in chapter 9 of the book. This is the list of section properties that you would get for rolled steel shape. For you civil engineers in the room, this is very, very relevant. Okay, so this is just a snippet of some of the data that you'll find in the steel manual for a variety of rolled sections in the manual. Just a little factoid so that you all are aware of how these things are named. If you have a shape that's like a W14 by 38, what that means is the 14 is about how deep it is. The depths can vary for shape to shape. And the 38 tells you how heavy it is. So it's 38 pounds per foot. But if you look at that shape, for instance, there's a W14 by 38 right here. You can see that the area is listed. You can see that the depth and width, but you can also see the moments of inertia are listed as well. And so it's helpful for you to understand what those values are. So for instance, for the moment of inertia of a W14 by 38, something like 385 inches to the fourth. How did they do that? They did that same algorithm we just did on that shape. So it's a it's a rectangle here, a rectangle here, a rectangle here. There's usually like a little fillet right there, and so on and so forth. And so they've already done all of that math for you and listed the value, in this table, this 385. This is a very, useful thing to be aware of. And for anybody who takes steel design, we are going to use this stuff in there. So it's definitely something to make sure that you're comfortable with. Any questions before we call it for the day? I know we're running out of time, but if there's anything quick. All right, on Wednesday, we're going to begin structural analysis. So some of the basic structural analysis that you need to learn from statics, and we're going to start with trusses. So trusses are our goal for Wednesday. That's all I have, everybody. I will see you all then. Everybody stay safe, stay healthy. We'll see you then.